Welcome back to trigonometry, and we're talking about the complex plane. Somebody left me a pretty drawing. I thought you'd like to see it before the t-shirt of disgust hits it. Ugh. And of course I still haven't washed the t-shirt of disgust. So I'm somewhat excited today, more than usual, because we're really getting into some interesting things. Complex analysis is just fabulous. And the more you know about it, the more interesting it gets. Let's kind of go back to what we started with. Here's the complex plane. So here's the x-axis, usually called the real axis. As I said last time, there's some slight technical problems with assuming that the things on this axis are actually real numbers. By and large, everybody believes differently than me that you can just say that this is the real number 1 and this is the complex number 1, and there's no real difference because real numbers are subsets of complex numbers. As I mentioned, from first order logic, I think there's an argument that can be made against it, but it is not practical to do so. For all practical purposes, this kind of exposition of this works. Here is the y-I axis, or imaginary axis. And this is just I, 2I, 3I, down here, 1, 2, 3, negative I, negative 2I, and negative 3I. Remember that I equals the square root of negative 1, therefore I squared equals negative 1. I cubed, which equals I squared times I, is negative I. And I to the 4th, which equals I squared times I squared, is positive 1. Very important to know these. When we put a complex number up, what is it? So let's put one up. How about, I'm going to try and pick an example here because I want to show you the really amazing things about this. And for this picture, I'm going to put up 2 plus 2i. Here's the real part, here's the imaginary part. So here's the real part, 2i, here's the imaginary part. Here is 2 plus 2i. Now, what we were talking about was, how do you say which complex number is bigger than other complex numbers? And complex numbers are not ordered by the way that you would think numbers. They're not ordered like real numbers are ordered. So what we did was, to figure out a way to order complex numbers, we take what's called a valuation field, which is way above where you need to know. But we take a map from the complex plane into the real plane by this. F maps the complex, this C is the complex plane, to the real plane by F of Z. And remember, so in general, we use Z or W to denote complex numbers. So F of Z is, and this looks like the absolute value of Z. This is the modulus. This is the modulus, and this is given by the square root of Z times Z bar, where Z, if Z is A plus IB, Z bar is the complex conjugate, is A minus IB. If we multiply these together, we FOIL these out, we end up that Z times Z bar is A squared plus B squared. And so the modulus of Z is equal to this, which is equal to this. This looks very much like the length of the hypotenuse of a right triangle, and it is. And this is where this is really useful. The modulus, so this is our Z right here in this particular case. The modulus of Z in this case is going to be represented by the length of this hypotenuse, or blue line. So this is, A is 2 here, and B is 2. So this is 2 squared plus 2 squared square root. This is the square root of 8, which is better displayed as 2 times the square root of 2. This is more efficient, I think, better looking at it. And my 2's and z's look a bit alike, so don't get confused at all. So what's the significance of this? Well, so think about this. What angle is this? And I'm going to call this alpha. Well, hopefully you see that just from the picture, the rise over run here, if this was in a regular XY plane, this is 2, this is 2, maybe I'll use different. So the height here is 2. The run here is 2. So what is tangent of alpha? Tangent of this alpha is 2 over 2 equals 1. Therefore, alpha is arctangent of 1. Hopefully you know that this is 45 degrees or pi over 4. For the moment, I'm going to use 45 degrees. And once again, you're going to wonder why we keep going back and forth between degrees and radians. It just kind of gets done that way. In what we're going to be doing now, we're going towards vectors. The truth is we're going to be using degrees a lot more than radians. And I think it is just the case that people are more comfortable with degrees in being more familiar. That's 60 degrees, and having some idea of where that is on the horizon, as opposed to pi over 3 radians. But anyway, so what's the significance of all this? How is all this related? Well, so let me give myself a little space here. You'll notice that, so the tangent of alpha, which is the tangent of 45 degrees, is equal to 1. What is the sine? We'll do this. So the cosine of 45 degrees is going to equal what? What do we got? Cosine is this divided by this, and you should know it's 1 over the square root of 2, but I'm just going to show you. This is the x part of it, which is 2, divided by the hypotenuse, which is this, 2 over the square root of 2. This is, of course, 1 over the square root of 2. And the sine of 45 degrees is also going to be the same. It ends up being 1 over the square root of 2. Let's think about what we can do with this. So if I call this r, and so r is the hypotenuse, what is r sine theta equal to? Or sine alpha, sorry, we're using alpha in this. Well, remember that sine of alpha is equal to y divided by r, so r sine alpha equals y. In this case, r is 2 times the square root of 2. Sine alpha is 1 over the square root of 2. This is equal to 2. What did this just tell us? We just figured out what the y coordinate was, 2, and we're in the y-I axis, so it's 2i. Absolutely similar argument, we can see that the x component of this is going to equal r cosine alpha, which is going to be 2 times the square root of 2 times 1 over the square root of 2, which is 2. These are called vectors. Vectors have a point in a direction, and they give a distance or a magnitude. And this is where we're going to start working into vectors right here. My producer tells me it's time to load up another reel. We will be right back.